Okay, so let P be a prime number. In the first part of this old question 16, we're asked to use congruences mod 4 in Z to show that if P is congruent to 3 mod 4, then P cannot be of the form a squared plus b squared, where a and b are integers. Now there's a big hint here, using congruences mod 4. When you see a hint like that, you should try your best to use it. It's usually a good idea. Now, we have a congruence mod 4 already. I mean, we're given that P is congruent to 3 mod 4. So, I think it's clear that what we need to do is to show that when you look at a sum of two squares, that cannot come out to be 3 mod 4. And therefore we should look at squares mod 4. If we're going to be looking at sums of two squares, naturally we should look at an individual square before we start adding them together and seeing what we can get. Well, the fact is, even squares are all congruent to 0 mod 4, and odd squares are all congruent to 1 mod 4. Now there are a couple of different ways you might confirm this. Obviously trial and error will suggest it. But one way is just to take every different thing mod 4 and square it. There are only 4 different things mod 4. So if we take 0 squared, this is congruent to 0 mod 4. 1 squared is congruent to 1 mod 4, obviously enough. But also 2 squared is 4, which is 0 mod 4 again. And 3 squared is 9, which is again 1 mod 4. Now everything is congruent to 0, 1, 2 or 3 mod 4, so its square will be congruent to 0 or 1 mod 4. Now an alternative is the following. An even number will be of the form 2k, and if you square that, this is 4k squared, which is congruent to 0 mod 4. Whereas an odd number is always of the form 2k plus 1, and expanding out the square of that, you get a multiple of 4 plus 1, so that's 1 mod 4. So one way or another, integer squares can only be 0 or 1 mod 4, they can never be 2 or 3 mod 4. Now if we add two of them together, well, the possibilities are 0 plus 0, if they're both even, or 0 plus 1 if one is even and the other is odd, or 1 plus 1 if they're both odd. I mean, the things that we're squaring, both odd. So the possibilities mod 4 are 0, 1 or 2 when we add two squares together. So that's it, we can't get 3 mod 4, so that's the first part. Now we're also asked to express each of 5, 13, 41 and 73 as sums of two squares. Now naturally we should notice what these are mod 4 if we're going to be looking for them as sums of two squares. Well, of these possibilities, obviously these are all odd, and in fact they're all 1 mod 4, so this certainly doesn't prohibit them from being sums of two squares. It doesn't guarantee that they will be sums of two squares, but if we check, then we can find, with a little bit of trial and error, fairly easily, that each of these is a sum of two integer squares. Now this one, that's going to have to be 25 plus 16, so yeah, that's 5 squared plus 4 squared. And the last one is, oh, that's a bit easier, I think 8 squared plus 3 squared. Now you also notice why these numbers mod 4, why pick out these ones? Well, these are examples of prime numbers that are 1 mod 4, and you might conjecture on this basis that any prime that's 1 mod 4 is a sum of 2 squares. So any prime p that's congruent to 1 mod 4 is of the form a squared plus b squared, where I mean a and b are integers. And a little more experimentation will reveal more examples where this appears, well, more examples that agree with this conjecture. But no matter how many examples you produce, you can never be sure that the next one's going to work. So we need a proof for this. This is something that was conjectured by Fermat and proved by Euler. There are several things like that. Now, there are other things we might say that are slightly different from this, but definitely not the same. So this is not to say that a sum of 2 squares is always prime and congruent to 1 mod 4. That's clearly false. And it's not quite it's not the same as saying that if a prime is a sum of 2 squares, then it must be 1 mod 4. We'd already showed that by, well, almost showed that by showing that if it's 3 mod 4, it can't be a sum of 2 squares. There's also the special case p equals 2, which is 1 squared plus 1 squared. But the implication the other way around, that if it's every prime that's 1 mod 4 is a sum of 2 squares, is a much stronger thing to prove, and that's what we're going to do.